Welcome you all to this cryo-EM course. Last class we discussed about the different types of focusing, that starting from focused, defocused, means under focused, over focused images, and then we also look at the actual power spectrum and images and what kind of differences we can see it. Now we are going to discuss little bit about the various pump system of the TEM and cryo-EM. So, generally 4 types of different pump or 5 types of different pump we can tell that we can use it for the TEM system or cryo-EM system. So, generally one of the common pump we use it, that is the rotary pump, and that is a very noisy pump, and then oil diffusion pump is the another one pump that I am going to discuss again. I will just have some couple of diagram and I will explain it, but most of the time nowadays in the microscope we are not using those pump. Even the oil diffusion pump also we are not using, because oil diffusion pump is creating lot of noise. Oil diffusion pump is can contaminate the microscope. It is not generating any noise, it is a very silent pump, and that is the reason the old microscope or some specific microscope we are using oil diffusion pump. Rotary pump is generating a lot of vibration as well as the noise, but current microscope most of the time we are using the turbomolecular pump and the ion pumps. So, we will discuss this. Before that we have to know that why do we need all the different types of pump in the electron microscope. If you do not use the pump, what is going to happen? So, this pump system is very important for the electron microscope, because we are generating electron and we are considering that electron. So, if you just remember that we discuss about that brightness of the microscope, and we are making a gun crossover point just near the filament, and then the electron is going through the accelerating stack, then it is a condenser lens 2, and then we are making the beam parallel, and this parallel electron, this parallel illumination is interacting with our sample, and then it is scattering in a different angle, and that we are recording in our images. Now, if our system is not under vacuum, it cannot generate a very homogeneous monochromatic electron beam which can go through the sample, and beam will be not parallel. There will be lot of other molecules will be there, air molecules, oxygen, nitrogen, or water molecules. The electron is going to interact with them. It is not going to directly interact with our biological science sample, and that is going to create lot of inelastic scattered electron, and that is going to create lot of noise, and as well as it is going to damage the filament also, because filaments are very expensive, and that is the reason the gun region, the column region, we need a very high vacuum system. Not only that, while we are inserting sample, if you remember, if this is our goniometer, and we are trying to insert the sample here. When we are trying to insert the sample here, there we are trying to connect the holder directly with the microscope column which is attached with the microscope, and there we are trying to insert lots of air and moisture inside the column. In that particular area, we need a turbomolecular pump to keep a good vacuum, which will help us to maintain the proper vacuum. So, those are the reason that we need high vacuum inside the microscope. Let us take a look what kind of pump we are using inside the microscope. So, I will just here couple of values are very important in the microscope. If you just consider that, okay, so most of the time if you go to inside the microscope, you will not see all these value that 1 torr, but this is good to know and connect. You should know how to convert from each other. So, 1 torr is equivalent to 130 Pascal, and 1 Pascal is 7.5 into 10 to the power minus 3 torr. And 1 bar is the atmospheric pressure, we all know that it is 760 torr, and it is equivalent to 10 to the power 5 Pascal. So, here generally for the electron microscope we are talking about couple of different type of vacuum, that rough vacuum, low vacuum, or high vacuum. Here you can see this is the rough vacuum. What is the value of the rough vacuum? If you just consider the rough vacuum value, it is 102.1 Pascal. or it is 1 to 10 to the power minus 3 torr. It is called the rough vacuum. So, comparatively low vacuum, if you just consider, it will be 0.1 to 10 to the power minus 4 Pascal, that means 10 to the power minus 3 to 10 to the power minus 6 torr is low vacuum. Now, near the gun area we need a high vacuum, and that is depending on 10 to the power minus 4 to 10 to the power minus 7 Pascal. That means 10 to the power minus 6 to 10 to the power minus 9 torr. So, generally for ultra high vacuum microscope we are using 10 to the power minus 7 Pascal, generally 10 to the power minus 6 to 10 to the power minus 7 zone is good enough, and generally the additionally, as I mentioned, that the vacuum in the gun area is 10 to the power minus 8. So, because gun is a very sensitive and very expensive material for that electron microscope, that is the reason it is better to protect that area properly. Now, here we can see different types of different types of pump. So, as I mentioned, that rotary pump, then oil diffusion pump, then turbomolecular vacuum pump, and then ion pump. So, here some of that pump different vacuum it is written. The rotary pump, as I mentioned, rotary pump is a very noisy pump, and how it is working in the next slide we are going to discuss that, but from the atmospheric pressure we can go to 10 to the power minus 4 torr. But the oil diffusion pump, it is a very silent pump, it is not generating any noise, it is using a oil which this oil will mix with a air molecule or water molecule, and it will go through this one. And then there is a turbomolecular pump which can start from the atmospheric pressure and go to very high vacuum. So, that is a very strong pump. Most of the cases in the electron microscope we are using the turbomolecular pump. Then when you will reach a certain vacuum, then ion getter pump will come into the picture and ion getter pump will start working. So, how these pumps are working and how these pumps are interconnected with each other, let us take a look. As I mentioned couple of times, the nowadays most of the microscope we are not using the rotary pump, we are not using the oil diffusion pump, they are not connected with the microscope anymore. This oil diffusion pump, so many cases the old microscope is connected with the oil diffusion pump, recent microscopes are not connected with the oil diffusion pump, and the contamination from the oil chances are very low. Most current microscope, it is connected with the turbomolecular pump or the ion pump. Let us take a look how this turbomolecular pump ion pump is working, and also let us discuss little bit about the that rotary pump or roughing pump, how it is working. So, here it is the most common roughing pump is a mechanical rotary pump in which a belt driven valve it is rotating, and it is helping us to remove the moisture or air. Let us take a look from the diagram. If you look at the diagram here, you can see this is our rotary pump or roughing pump where there is a valve, and this valve is closely connected with the wall, and when this is the inlet, this will connect with any chamber or any device which we really want to see under vacuum, and this rod will rotate very tightly through this. When this rod will rotate, and this is the rotor and this is the pump chamber, and this is the casing of the chamber casing. Now, when this valve it will rotate in this particular direction, whatever the moisture or air coming from that particular device, it will be here written here, and this valve will move entirely to this direction. When it will reach here, this valve will rotate from this direction to this direction. You can see this entire chamber, it will be opened up somewhere here, and whatever air moisture or rest of the pressure, it will come here, and this will try to pressurize this exhaust valve, and this exhaust valve will open up, which will help us to remove that moisture. And this is the rod, it will rotate in this direction constantly and trying to remove the excess moisture or air. But this pump is generally very noisy pump. Generally it should not keep with the microscope, because there will be a vibration because of this pump, and which is going to affect our imaging system. What is the next pump? As we mentioned that the next pump is the diffusion pump, or it is called the oil diffusion pump. Generally this oil diffusion pump is giving us a very high vacuum. How this oil diffusion pump is working? So, oil diffusion pump, you can see there is a heater is connected, and there will be oil inside that pump at the bottom of the pump. Now, this is the chamber of that pump. If you just look at this, this is the outlet, and this is the inlet, where this inlet will be connected with the microscope at the bottom part of the microscope. And all the cases you can see there are some valve will be there, which is connected with the lower part, and it will keep the system closed. If there is a oil is heated and it will make some kind of vapor, that will create a pressure and it will open up those valves, otherwise it will be stay in a closed condition. Most of the time all these cases we are using some synthetic oil. And now the outer part of this pump, we have a cooling water coil, where the cold water will go through this pump and it will maintain the very low temperature of this outer part of the pump. So, that will help us to condense the air molecule and water molecule, and that is the reason we are using this kind of cold water. Now, this is the jet assembly as I mentioned, and now this is the outer part of the pump. As I mentioned that this is the outlet, where that oil and oil trapped with the moisture or vapor, that will go out through this channel. Now, when this pump will start working, first that okay, this is a heater and will heat that oil. When you will heat that oil, after a certain temperature, there will be a lot of oil vapor, it will come out. This oil vapor, it will create pressure on this particular valve, and some of the oil vapor, it will come out through this valve. Now, other oil vapor, it will go and it will create a same kind of pressure in this valve, and the vapor oil, it will come out through this. When this vapor oil, it will come out, there is a cold chamber outside, because cold water is passing through this chamber, and when this oil vapor will come closer to this chamber, they will condensed. When they will condensed, they will deposit in this chamber again. Now, you can see gradually when there is a more and more vapor is coming, it will go up and interacting this valve, where it is connected with the microscope. When it is connected with the microscope, you can see that there will be some vapor or air molecule will be stored in the will be there inside the TEM, which will come down here and it may interact with this oil vapor. When it will interact with the oil vapor, it will be mixture of the oil and vapor mixture, and when it will come closer to this one, you can see they are going to condense some of the oil, it will deposit here. Otherwise, this vapor which is trapped, this oil vapor which is trapped with some water molecule or some gas molecule, it can find out another outlet through this one. It will just try to go out, and because of this water molecule, those things will condensed here and they will go out through this chamber. So, in this way we are using that oil vapor which can interact with the air molecule, which can interact with the water molecule or vapor, and then condensed through this chamber. When it will pass through this area or chamber, it will condensed and follow a outlet path and go out from the microscope. Why we are interested about the oil diffusion pump? Oil diffusion pump we are mainly interested because oil diffusion pump generally giving us a very high vacuum and it is not generating any noise. Why we are worried about noise? Most of the time those microscope, if you look at this part, this inlet from the microscope which will be directly connected with the microscope, and when this pump will work and if it will generate a noise constantly and this mechanical noise, this vibration, it will transfer to our images, it will go to the detector and our data quality, it will be really bad. That is the reason whenever we are collecting a data, we need a noise free room. Even noise should not come from AC or any other environment. So, definitely when if the pumps are attached with the microscope and they are generating lots of noise and vibration, that is going to affect our image quality. That is one of the reason we prefer those pumps which is not generating noise and we can get a very high vacuum. So, oil diffusion pump is one of that which is not generating too much noise and giving a very high vacuum. But the major problem is that sometime because of this oil, it is contaminate the microscope column with oil. That is one of the reason this is not a very favorable pump nowadays we are using for the keeping high vacuum for the microscope. On the other hand, we are using turbomolecular pump. Turbomolecular pump is a very good pump and we are using this pump to maintain a high vacuum. Let us take a look how this turbomolecular pump is working. So, this is the overall architecture of the turbomolecular pump. If you look at this, this is the upper casing, and if you just remove the upper casing part of this turbomolecular pump, where you can see these are the multiple blades and this is a stack together. This is the internal view of this turbomolecular pump. So, here you can see turbomolecular pump without casing and turbomolecular pump with casing, which is nothing more than a small turbine that rotates at a very high speed. So, this is a turbine which is rotate at a very high speed and it is trying to take out all this gas molecule whatever is coming from the microscope, and through this blade it will just push that electron. So, those blades are constantly rotating very high speed. When these blades are rotating very high speed, those blades are putting it in certain angle. So, if there is a air molecule is here, this air molecule will pushed by this blade because it is constantly rotating. When there is a high speed rotation, this high speed also going to push that air molecule very strongly towards the next blade, and the next blade it will push that air molecule or water molecule towards the next blade, where the next blade push it out to the next level of the blade. So, this is how constantly air molecule is coming from the microscope. It will be pushed from one direction to the other blade and go through like that. So, here those blades are constantly pushing this molecule air or water vapor, whatever it is, it will push through those blade and go out from the microscope setup. So, like a jet turbine, it pulls air in at the front end and force it out to the back. So, the blades are designed like a airfoils to enhance the flow of the gas through the system. That I was trying to explain, that the blades are in a certain angle. So, if one water molecule or air molecule is pushed towards the that there is a certain angle, this blade will push towards the other direction, and this is how constantly this blade will start pushing the air molecule and throw it out from the microscope system. So, this pump is working from normal air pressure to a very high vacuum. Generally, this is connected where we are inserting the sample, because that is the one area we are daily basis breaking the vacuum. So, we need a pump system which will start immediately when you will insert the holder and throw out the throw out the gas molecule, air molecule from the microscope. So, that is the good setup, that one from the atmospheric pressure we are going to very high vacuum, but the drawback of this pump is that this pump itself is a very noisy pump. So, it is generating lots of noise. So, because this turbine when it will rotate, it will generate a noise, it will generate a vibration, and that is going to affect our imaging. That is one of the reason when we use this pump, we use this pump in such a way that will reach a certain high vacuum, and then this pump will stop automatically, and then we will go back and use another different type of pump, that is called the ion pumps, and that pump will work in a very silent mode. So, turbomolecular pump will work, it will reach from 0 vacuum, means atmospheric pressure, to 10 to the power minus 5, 10 to the power minus 6. As I mentioned here, if you just look at here, so it will reach that 10 to the power minus 5, 10 to the power minus 6 torr. Now, that ion pump is going to come into the picture. Let us take a look how this ion pump is working now. So, ion pump is a very specialized pump, and this is a very expensive pump also. It cannot work in a normal atmospheric pressure. Okay. Why? I am coming back to that later. So, now look at this, this is the overall architecture of the ion pump. So, this ion pump, this is the casing of the ion pump, and the ion pump is made by titanium ion. So, there is a cathode and there is a anode cylinder. You can see this is the anode cylinder and this is the cathode. This is a cathode which is made by a titanium ion. Now, when there is a very small amount of gas, this gas will go inside, and there is a high voltage where you have a cathode and anode, which will help us to ionize the gas molecule into different ion. It will be a positive ion, it will be a negative ion, and now this titanium is going to play an important role here. Titanium is going to interact with those ions. So, if you just consider that water molecule is there and water molecule is ionized, H plus OH minus, and then this other air molecule is there, that will be also ionized, and now this titanium will interact with them, and then from the titanium oxide, and then trap those gas molecule with those ion. So, here you can see those gas molecules are ionized, titanium is interacting with this, and they are trapping them on the wall. So, in this wall you can see it is not only the titanium ion, it is interacting with that gas and the other molecules and trapped there. So, trapped all of this. So, the gas molecules, the buried gas molecules atom are showing here. So, that interact with the titanium and staying there. So, that is one of the reason I told that this ion pump cannot work at a atmospheric pressure. Why? Because at atmospheric pressure there are so many gas molecules are there, and whatever we are making here this titanium, that is a limited number of ions are there, atoms are there. Now, if we have started this ion pump in a normal atmospheric pressure, there will be so many gas, it will be ionized and it will be interacting with those titanium ion, and those titanium ion will be completely exhausted with those gas molecules. So, that is one of the reason we cannot start ion pump at the beginning. So, we need little bit time, that when we reach a certain vacuum, that 10 to the power minus 5 torr or 10 to the power minus 6 torr, where we have a very high vacuum is there. Now, we want a ultra high vacuum or we want a very good vacuum for the gun, that times ion pump will start. So, forcefully in our lab, if there is a microscope crash and forcefully I am starting the ion pump from the beginning, it is going to exhaust this ion pump completely, and then entire ion pump will be damaged, and that will be very expensive. That is the one of the reason ion pump we cannot start at beginning, we have to wait little bit and then we can start the ion pump. One thing you have to also remember that ion pump sometimes it is called the trapping pump, because this ionized gas it is interacting with the titanium ion and then fixed there. So, that is called, that is one of the reason it is called the trapping pump also. So, ion pumps do not contain oil, so they cannot contaminate the TEM column. They also have no moving parts. So, relying solely on the ionization process to remove the air. So, that is the two good thing, that we do not have to use oil to contaminate the column, as well as this is a very silent pump, there is a no moving object and only depending on the ionization of the gas molecules. The ion pumps emits electron from a cathode. These ions spiral in a magnetic field and ionize air molecules, which are then attracted to the cathode. The energetic gas ions spotted the titanium ions from the cathode and they condensed throughout the pump chamber, mainly on the cylindrical anode, trapping the gas atoms. Thus, the ion pumps remove gas atom in two ways, by chemo. Okay. So, ion pump here we will just discuss this. Ion pump can remove the ions in a two different way. It is trapping the gas molecules and attract to the anode surface and deposit there, and the smaller the ion current between the electrodes, the lower the vacuum. So, the pump act as a own vacuum gauge. Okay. So, now take a look at this. I was already mentioned that exhaust pump and the trapping pump. Now, we will just discuss about the one more pump, that is called the cryogenic pump. What is the cryogenic pump? As the name implies, the cryogenic pump is a cryopumps rely on liquid nitrogen to cool the molecular valves, large surface area. This cold surface efficiently remove the air molecules as well as the small amount water molecule from the ambient pressure down to 10 to the power minus 4 Pascal. Because they are oil free, cryopumps are also used to bake ion pumps and prevent their accidental contamination through bake streaming from oil bearing pumps. So, we are not going to these technical details. Always remember that okay, we are using some kind of cryogenic pump also, where we are using liquid nitrogen to trapping the water molecule and ions to remove those kind of contamination. Now, take a look to that what is the entire pump system of our microscope. Here you can see this is the entire pump system of our microscope, where there is a ion pumps are connected near the gun area, as well as ion pumps are connected in the column. The turbomolecular pump is the mechanical pump what we are talking about here. This mechanical pump is connected, or turbomolecular pump is connected near the sample insertion area. There is a diffusion pump, that is I was telling that oil diffusion pump which can contaminate. So, some microscope we can find out this diffusion pump. Nowadays those things are not there, only the mechanical pump is working. There is a buffer tank or vacuum reservoir which is loading all this air molecule or moisture in this vacuum reservoir. This is overall about this vacuum system, how this vacuum system is working in the electron microscope, and that is very very important for our imaging purposes also. If we do not have a proper vacuum or high vacuum, it is going to affect our imaging system. So, I will finish today's class here. We will discuss more about the detector in the next class. Thank you all for your attention. Next class we will start with a detector.